Good afternoon and welcome to this webinar. This webinar is provided by Bob Willis Online. My name is Bob Willis and I'll be running today's session. Now, the control panel allows you to do a number of things during the presentation. First of all, you can open and close the control panel by clicking on the orange button. This provides you with a view of the slides. You can go full screen or either on your PC or on your projection facility in your conference room by clicking on the button as indicated here by the red arrow. Now, if you have any questions at any time during the webinar, all you need to do is type them directly into the control panel, and I'll do my best to answer those questions at the end of the webinar this afternoon. Sometimes it's easier to type a question while you think about it, and possibly if you have a colleague in the room with you. Just a reminder, if you have any technical issues, please use one of the telephone numbers provided on your registration and reminder emails. You'll also need your webinar ID number and access code, which was included on your email. It's not possible for the presenter, myself, to assist you during a live presentation. And just a reminder that as the internet is under considerable pressure, your area or factory may have bandwidth problems, which may slow down the presentation or presentation content. If you have any issues, it's best to log in and then go back to the screen again. At the end of the webinar this afternoon, we have a couple of survey questions. If you just take a couple of moments to complete that, it gives us feedback on the content, the presentation, the organization, and of course, things you might like to hear about in the future. You'll be receiving a copy of the slides shortly after the end of the webinar. And just a reminder, if for some reason you don't see a copy within a few hours, then just check your junk folder. 9 times out of 10, that's where it ends up if you don't receive it on the email directly. So once again, thank you very much for participating in this event. Just a little bit about my background before we start talking about our subject today, which is robotic soldering. I've been involved in electronic manufacturing all of my working life. As a mechanical engineer, I've had the pleasure of running training courses, seminars worldwide on electronic manufacturing for a variety of different organizations and companies. I've written a couple of textbooks, created videos, interactive CD-ROMs, and a variety of other things within the industry. And it's something I love doing, and I love getting my hands dirty because it's the best way of learning. So that's just a little bit about me and my background. Just mention our final 2 webinars coming up, our monthly webinars, one in November, which is what is a good solder joint and how to test it, and a guide to surface finishes, that's in December. We, of course, have a whole program of events for next year, and of course, you can always book a webinar on demand or look at our archive webinar service. This is kind of a special webinar specifically today on robotic soldering and a little bit about the robotic soldering experience. So hopefully, you're going to enjoy it, and hopefully there'll be lots of good questions. So first of all, my first experience with robotic soldering goes back to 2003, and I was invited to a company in Germany who had a soldering problem. And I was working for one of the material suppliers. But it wasn't actually a robotic soldering problem, it really was a solderability problem, as you can see in these 2 photographs. The metallization on the ceramic hybrid was not really suitable for the application, and consequently there was the problem, not the machine doing the work. So often the case in many process issues when you look at them. So in terms of the robot experience, just a little bit about that first of all. It's something that I've put together with a couple of colleagues. And the whole idea is bringing together suppliers of robotic soldering systems, materials, in one area and building some test boards. So that's the hands-on feature, and that will be done under COVID guidance. And it's something that we'll be announcing dates on in the future. After that, the content of what we do will form more webinars, more technical presentations on more specific areas of design, manufacturing, materials, etc. And that will form part of a webinar or webinar conference along with interviews from our partners. So that's a little bit about the experience. And of course, if you want further information, there is a link here, which I've highlighted on this slide, and it'll obviously appear on the slides that you receive. So you can participate in two ways, as a partner or as a delegate on the conference. And the board that we'll actually be building is just a simple test board that I put together. It features 18 connectors on a 2mm pitch. You've got thermal isolation of different types and separation from the inner layers on the board, and of course just some straight through hole soldering terminations, and that'll be on some different surface finish boards that we'll be building. So that's a little bit about what we're going to be doing in the future and what our plans are to expand the general knowledge on robotic soldering and to demonstrate different technologies and materials to boot. In addition, you might be interested, and these are already available on the Winnie website, but also on my own YouTube channel, Defect of the Month. I put together a series of defects specifically related to process issues or process trials that I conducted on robotic soldering. So you can watch any of these video clips if you wish by visiting the website. Again, I've posted them in a variety of different locations. So hopefully they are again a useful resource for people getting into this technology. So I want to mention just a few things in terms of the benefits or potential benefits. There could be a much larger slide, a lot more topics, but I just wanted to mention a few to start off with. And as we go through this presentation, we'll probably indicate a number of others as well. But some of the benefits are cost reduction, and this is cost reduction through using perhaps a smaller piece of equipment or multiple pieces of equipment as an alternative to traditional processes that are used for the soldering of through-hole terminations. As many of you know, I wrote a book on intrusive reflow, so that's my first love probably, but I've got a lot of interest now in robotic soldering. Also, it allows us to create work cells. So one production operator could run 2 work cells, which could incorporate 2 or maybe even 3 robots. So loading boards to the soldering station and then moving on to the next one and removing it. So you're creating a cell. It gives the ability also for production staff to upskill, to gain new experience in something which is fairly new even to a lot of process engineers. And also, it allows you to perhaps evaluate a new technique. So robotic soldering has been around for quite a few years, but it's new to a lot of people, and I'm still learning every day about some of the issues and some of the ways of improving the process. So consequently, learning a new technique that you could introduce in your own manufacturing environment may be beneficial. So just as an example, this is a video clip from a company which has implemented contact soldering on a number of cells on a production line. So just a simple example of what can be done. And of course, there are more advanced lines that you'll see in other areas. Now, this is partly, I'm going to be telling you about some results that we achieved a few years back in 2014 when I worked with Dr. Chris Hunt of the MPL on a high temperature soldering project. And one of the 2 reports, which you can freely download from the MPL website, goes into our experience with robotic soldering, but using high temperature alloys as opposed to just traditional lead-free alternatives. Again, we'll mention some of the results that we got in that study as well during our webinar, our time together, but you can find out more of both of these reports free of charge from NPL. So a little bit of information that we gathered from a previous webinar in terms of a survey, and we'll be running 4 mini surveys today, and you will receive the results of all of those. But the last time we conducted this survey, we asked, do you use robotic soldering? And as you can see here, it's a fairly small percentage of companies using robotic soldering, either laser, contact, or both, but a high percentage not using any of these techniques, which is not unsurprising, but hopefully the result on this particular question, when I pose it later on, will see quite a dramatic change, I believe. In addition, we also looked at the materials that people wanted to use. And again, on one of the survey questions that I'll ask this afternoon, we'll look at that. You know, what materials are key for you to use? We were in fact concentrating on the higher end temperature, or higher range temperatures in the previous survey, but you've got the opportunity for low temp as well when we come to that particular question. Now, the things that we did on the NPL project using robotic soldering, but also using hand soldering and selective soldering as a comparison, we assembled polyimide boards. And the reason for using the polyimide boards originally was because the product was going to be exposed to high temperatures. And as you can see here, we built boards with different solder alloys. We also built some boards with intrusive reflow technology and epoxy materials for other surface mount components, which won't be discussed this afternoon, but is in the reports that I mentioned. We then took the boards and exposed them to 200 degrees C for 500 and then 1,000 hours in a static oven, microsections, X-rays, optical inspection. And we did other testing on the boards as well to understand the effect of thermal shock and peel strength results on other substrates, materials, and copper foils. So there's some other material in the other two reports over and above the specifics relating to robotic soldering. And I always like to show this slide and apologize to anybody who supplied me boards and connectors for this particular study. They don't look very attractive after you've stored them for 200 degrees C for 1,000 hours. So I apologize to Merlin and I apologize to Harting on this particular occasion. But thank you, they still work perfectly. So the polyimide construction is here. I won't go through it because you've got it as a reference. So you can see the standard construction we used on our test boards. And we used 4 different materials on the NPL project. The project involved simply soldering this 96-way connector. It's a high temperature connector. The connector was in fact held in place with clips at both ends, allowing us to rotate the board and solder. And as you can see here that we did have 2 different types of pins, a square pin and a more flat pin on some parts, and that's all to do really with cost reduction when you're manufacturing connectors. Connector pins used to be round, which was nice and easy to calculate hole to lead ratio. Then we went to square, and now more commonly we use flat punched connector pins. So in terms of design rules, now on the new board, the board I'm using for the experience, and also on this board, we used what I call my standard design rules. So it's the maximum pin size plus 0.010 of an inch gives me my finished hole size. I use this for all types of soldering operation. Standard pads, but with robotic soldering, with some of the simpler robotic systems, you might want to extend the pads slightly, have a slight tail to it, have a pear-shaped pad perhaps, and this allows you to actually have a landing position. So rather than hovering above the surface of the board, that some companies and some systems allow you to do very successfully, if you need to come in contact with the board surface, then again you've got a landing area which won't damage or catch the edge of the pad. You're actually coming down to the pad area. In terms of solder mask rules the same. So standard pad dimensions, solder resist 0.006 of an inch larger than the pad size. It is possible also to use resist defined pads, and sometimes that is done on smaller pitch connectors if you're doing drag soldering with a robot. The reason being that You're still making contact with the pad, still transferring energy to allow the soldering operation, but minimizing the possibility of lifting of the pads. And there are a number of other reasons for through-hole why we use resist-defined pads as well. The key thing is controlling thermal breaks. So we all know that if you have large thermal breaks and small thermal breaks, there is a difference in the heat up time and the transfer of solder through the bulk of the board. So if you've got a lot of copper connected to your through-hole, it's going to take longer, or you're going to need a higher temperature. So by adjusting those and maximizing to what the designer wants, but also what the process engineer wants, that's a key thing to get the best results. And we've done that on the test board that I'm using in Experience, and we also did that, as you'll see in a few moments' time, on the boards that we built at NPL. So basically, connectors, standard through-hole terminations, modifications, if you wish, on resist and pad dimensions to aid the soldering system that you might be using in your product or your process. I mentioned thermal breaks. This is an example of a thermal break in the inner layer. So our test board is a 4-layer board. It could be more, but a 4-layer is economical for this particular application. And you can see the same hole size is being used, but we've increased the separation distance between the copper and the inner layer copper, or we've reduced the track width, or we've reduced the separation, and using perhaps just one connection or 2 connections or 4 connections. And these variations are incorporated into the test board to see the effect on soldering parameters. It's a standard thing that we do. If you look at this in X-ray, for those of you who are not familiar, this is what you might see. You can see the individual terminations fanning out from the solder connection area. And I normally use this photograph to explain to rework operators why they're having such a hard time, and of course, obviously blame the design engineers for it, but there you go. Now, in terms of assembling a board with a connector in, the one sort of fairly simple thing that we've got to consider is how the connector stays in the board. Now, it won't just be connectors, it can be any through-hole component, but you've got to think about how you hold it in position. If you've got a connector which has retention clips, then that's nice and easy. You can flip the board over and you don't need any other tooling. If you can't do that, you might need a pallet. So you might load the connectors to the pallet, load the board to the pallet, and then run that through your process. But equally, you've got to think about the pin position and the consistency of the pin position. So if you've got manual cut and form pins, they're inevitably going to be in different positions. So if you are programming your system to make contact with a pin, then that could be an issue where you get inconsistency. So just think about the relative pin position in the plated through hole, the length of the pin, etc. So very trivial issues, but can become major issues if you allow them to do so. Now, there's a variety of different solders out there. These are the solders we used in the NPL project. As you can see here, there are the traditional lead-free materials, as well as some of the higher temperature materials. And one of the things that I want to do is do some work on low temperature alloys because they're becoming available with cores in. So you can actually get cored wire, but low temperature, reflowing 138, 139 degrees C. But that's not something I have done at this moment in time yet. But these are the materials that we used in the NPL study. Now, in terms of soldering, for those of you who are new to high temperature materials, this is just an example of an operator soldering through hole manually. And this is what we did on our study, manually first of all. And as you can see that during the soldering operation and then the solidification of the solder, the visual appearance can be slightly different. For those of you who are familiar with lead-free, they're slightly shinier but slightly duller in the surface texture when you look at the higher temperature alloys. And it's the same when you're looking at through-hole fill. When you're doing manual soldering or robotic soldering, if you're using the higher temperature materials, you do get or can get variation. And as you can see here, although these joints are perfectly good, there is certainly variation in hole fill. And you certainly get that when you start to use high temperature solders with hand soldering. And one of the things with hand soldering or robotic soldering, just remember that when you've made a joint, if you go back and try and add a little bit more solder, because you're not actually adding flux to the opposite side of the printed circuit board, the visual appearance will be different. And here is a good example of me touching up a joint, and you can actually see that you question the wettability or solderability in this example, but the one thing that was missing is the flux. There's no flux left to improve that result. So just a thing to think about. Try and reduce the possibility of going back and attacking a joint for the second time. Now, another quality control and process tool that I've used over the years is IR to do measurement and assessment. And this is a beautiful technique. So if you have an IR camera within your facility, it's a useful tool. What it allows you to do is see the hold time in terms of heat in the board, the residual heat, if you like. So if you've got a difficult to solder position on your board, you can always jump over it, go back to it, because you've put heat in that area. So you might solder 2 connect contacts, skip 1, go to 4, 5, 6, 7, come back to 3 again. And again, you can do the same sort of thing with robotic soldering. That's the beauty of it. So if you have an IR system, then use it, because it's very, very useful for a number of applications with robotic soldering, which I'll mention. So just a quick example. These are perfectly good joints that have been produced with high temperature materials successfully in manufacturing. Now, I mentioned that the study I did at MPL involved a number of different robotic companies providing contact soldering and also laser, and I've listed them here for your reference. And again, the material suppliers are also listed. So again, you can look at the report from MPL and assess that later on. But we'll look at some of the results during this webinar. Now, before we go any further, what I wanted to do is just run my first poll. Now, what I'm going to do is set up a poll, and I'm going to launch it. And the question is, what do you see as the main benefit of robotic soldering? So what do you see as an engineer, the main benefit of robotic soldering? So again, if you just like to click one of those answers, whichever you think is the most appropriate, we have a couple of hundred people online. So what I'd like to do is just leave that for about 15, 20 seconds, just to give everybody the opportunity of participating. So again, if you just like to select one which you think is the most appropriate, which one you feel will give you the most benefit when using robotic soldering. We're up to 75%, we're up to 80% of people voted, we're up to 85%, so we'll stop it there. Okay, so what I'll be doing is sending the results of these out after I've compiled them. So again, you'll get a copy of those in a couple of hours, probably after the webinar this afternoon. So moving on, so let's start to talk more specifically about robotic soldering. So what are the benefits? Well, flexibility. We've had flexibility from selective soldering for many years, allowing us to make changes to joints as opposed to wave soldering. But robotic soldering allows us more flexibility on creating joints. It allows us to give parameters for each individual joint if that is appropriate. Hopefully that's not. You really want to try and balance it as much as possibly from a thermal point of view. Using different tip designs allows you to do traditional soldering and drag soldering, which a number of robotic soldering companies have demonstrated successfully. You also got the choice of between contact and laser, and certainly laser is faster than contact soldering, but again, you've got to understand the technology and obviously evaluate the materials. There's been great strides in improvements in the use of and the development of cord solder wires. One of the big problems that we'll talk about is been solder balling using robotic soldering, primarily because the technique that we're using with robotic soldering is slightly different than you would with hand soldering, and of course everybody wants to go faster with a robot. As opposed to just work at the same speed as a production operator has done in the past. Nitrogen support is something that people discuss, but people assume that it's just related to improving the wettability or solderability, but it can actually help heat transfer as well, and that's where my IR camera comes in. The tip and tip control and the tip temperature control has been improved significantly from different suppliers over the years, and the ability to feed back information to the computer system and store that information, it can be invaluable in automotive, in high reliability applications, because you've got true traceability of the process. So that's an advantage to many people. One of the things that a lot of people forget about is accurate tooling. A robot, you tell it where to go, you tell it what to do, but if what you want to solder is not in the right location or not in a consistent location, that's a problem. So concentrate and make sure you organize or select a system and the appropriate equipment to minimize variation in relative position of the joints you're trying to solder. Don't underestimate this as something you need to look at. So just a couple of examples of robotic systems operating, and what you can see on the left-hand side is a laser system where we're producing joints, and on the right-hand side you can see an inline system which has been added to a conveyor. So you can see the joints being produced on the left and obviously on the right, and these are just two examples of robotic systems in the marketplace that I was using in my original study. In addition, just a couple of other examples, just so you've got a feel for visually what we're looking at, what you might expect to see if you were doing any trials yourself. These videos clips that you're seeing here are all from my test boards. So you've got contact soldering with the solder being added to the joint, and just below it you can see the same board being obviously soldered on a separate system but using laser technology, and that's on MTA. Here you've got Japan Unix, and on this first board we're actually doing drag soldering, so special tip, and we're drag soldering on a 2.5 pitch connector, so one row. And on the bottom video clip, again you can see my same test board, and we're doing laser soldering to the individual joints. So that just sort of gives you a feel for what we're talking about in terms of the process that we're using for this technology. So if we just flip back for a second and remember that when we're doing a soldering operation, we're basically bringing a tinned bit to the joint area. We're introducing solder to the joint area, normally from the opposite side if we're talking about manual soldering, and this makes sure that the joint areas to be soldered are up to temperature. This is how I train people how to hand solder. This is the fundamental way you do it. But with robotic soldering, you may be introducing solder in exactly the same way. You may be introducing solder directly to the soldering iron tip, or you might design your system to have quite a wide tip which is coming into contact with the surface of the pad and also the contact position, and then add the solder slightly offset. So again, offset onto the face of the soldering iron tip. And this overcomes some of the variability that you can get with pin position. So these are sort of subtleties that you need to practice and learn about when you're doing your robotic soldering, and particularly your programming, and when you're talking to your suppliers. But this is fundamentally what we would do. So just to give you a feel for some parameters, these are sort of typical parameters that you might come up against during a soldering operation or a setup operation. And these are sort of parameters that I used in some of the studies that I did at MPL. So you can see sort of typical cycle times, etc. And on the laser side, again, you can see the cycle times, the delay times, the energy being used during the soldering operation on that 96-way connector that I mentioned previously. So let me just step you through. If you're looking at contact soldering, i.e. a soldering iron on a robot, just to break it down into simple terms, we tin the tip. We may have cleaned the tip, and we'll look at cleaning a little bit later on. We bring the tip into contact with the pad and pin, or just the pin. And when that gets up to temperature, because we've done the previous trials or done direct measurements, we introduce the solder to the opposite side of the joint, as we would do with hand soldering, or alternatively adding it to the surface of the tip. And that's fundamentally how the soldering operation is done. So if you look at this example, you can actually see a wider tip being used, and the machine operator or the machine setter has set up the solder to add to the tip, the soldering iron tip, but it's slightly offset from where the pin is. So again, it's all about setting up the process which is most appropriate for your particular product. Now on the laser side, again, you can see in these multiple photographs which have been taken from one of my video clips, you can see the board and you can see the solder wire above the surface. So what's actually happening here is we're introducing a small amount of laser energy to the board to preheat it. And when it's up to temperature, we introduce the solder and then continue to feed the solder based on the volume required to fill the hole and, of course, give you ideally top and bottom side fillets, which is obviously what we ideally want in our process. So if you look at this example, again, another video clip, you can just see a practical example on a printed circuit board. And here you've got a number of different through-hole terminations being soldered. So there's no soldering iron, you're just using the laser energy, and adding the solder to the joint to finish off the product. So in terms of how you get the information to be able to continue that soldering operation, then of course each of the different suppliers have different levels of software to allow you to capture information. So you can either teach it, and this is slightly laborious in teaching a board, or you can draw in the board, and there are different levels of sophistication in the software which is available within the industry. But this is just an example of one of my old test boards. You can see at the back, you can see the connector being drawn in, and it gives us the locations, and then we can go in, select the individual pins, and then set up the parameters that we want to use for those particular parts. Now, ideally, all of those parts would be the same basic parameters in terms of time and temperature. But as I said earlier, if you've got different thermal breaks, which is what we've got on our evaluation boards, there will be a difference in the required settings, if you like. So this screen is actually from another machine, and you're looking at a soldering operation being conducted. But this one is actually capturing the temperature as well. So using, again, an IR camera on the system, it's actually capturing the profile that's being used. I have never done a comparison between the data captured and the actual, which would be nice to do, and it's something I want to do, but certainly this is very useful for monitoring the process and obviously understanding any issues that might occur in the manufacturing process, if the system can allow you to do that. And particularly important for, as I said earlier, high reliability applications. So just another couple of examples before we take another survey poll. So these are a couple of examples of, again, some of my trials on the 96 pin connector on a multi-layer board. And you notice on this, and you'll also notice on the next example, there is a lot of flux. Now, remember that some of the materials we were using on these studies were high temperature materials. And because we're talking about high temperature materials, the basic material does have a high flux loading. So we're not talking about traditional lead-free, and most cord wire manufacturers have significantly improved, worked very hard, not only for just traditional hand soldering with lead-free, but also for robotic soldering. So you will find differences in the amount of flux which is present on the surface of the board. And if you think about, these studies on high temperature were done in 2014, there's been a lot of development since then. But fundamentally, the soldering performance was good. You just got to look at perhaps the necessity in these examples, because of the alloys, needing to clean the product for visual and possible reliability reasons. So that's just a couple of examples of what you might expect if you were doing very high temperature materials with either of the different processes, but also there is a significant improvement in the amount of material left behind with the materials which are now being introduced. I'd like to move on to another survey question. So this survey is, do you use robotic soldering? So out of the 200 people that are online with us this afternoon, wanted to get a feel for what you're doing, what you're using. So if you'd like to just select one of the answers, so either laser, contact iron, using both techniques, or none at all, just give us a feel for what you're using. So we're up to 60% already have voted. So if you would please just select one, which gives us an indication. Again, as I said, I'll be sending the results of the survey out to you, so you won't miss anything. But it's just useful, so you've got a feel for what's popular, what's the most appropriate system to concentrate on, perhaps, or if both are popular, then you'll have to look at possibly investing in both. That's up to 85%, so I'm going to close the poll at that moment in time and move on to the rest of the presentation. So, cord solder wire. There's lots of good suppliers of materials out there. You've got to look at the size, and typically some of the materials I used in my study were 1mm, 0.8 and 0.6. So those are the materials that I use. And you'll find that nearly all of the suppliers can handle that sort of range and possibly smaller. There hasn't been any trials on low temperature so far, and that's one of the reasons that I'm very keen to see some results on some materials that I've got. But cord wire has obviously got flux in it, and flux is volatile. Now, the suppliers have, as I said, taken quite a lot of effort to improve the performance. So we'll try and understand what the issues actually are. But if you look at a cord solder wire, now I'm just showing an old video of mine where I'm reflowing 2 bits of cord wire, one with 1 core and one with 3 cores, and you can see the poor guy on the right-hand side crying as he disappears and falls away. But it just gives you an idea of what's actually happening. So the flux flows out from the solder wire, and if we can control that in some way, then we can control and improve the soldering performance. So if we take a printed circuit board, and this is just an example of a test board which has got some fine pitch packages on as well as simple through hole. One of the problems potentially you or anybody could face with robotic soldering is solder balls. And this is just a couple of examples on trials of my own. So what I've done here is circled the solder balls. And this is a well-known issue. And if you step back, it's been around for quite some time, and it still is today. But we can control this in 2 or 3 different ways. That is the reality. And part of the reality is adding the solder directly to the surface of the soldering iron tip, which is an elevated temperature. This causes spitting. Trying to go too fast increases the possibility of spitting. So you will find, if you go into some factories, some companies, the way they've gone to overcome the problem, or perhaps temporarily improve the problem, is cover the board. So in this example, you've got a cover plate. And I've worked in two factories like this, where we're just using a cover plate. So we're soldering 2, 3, or 4 connectors on a board or other terminations, but we're protecting other areas to prevent any solder balls landing on the surface. And this is particularly true of the automotive industry. So it's an extra thing that can be done, and it can be done as a temporary thing. Not ideal, you don't want it forevermore, because it does restrict the way in which we can effectively use some of our tools. So if you look at solder wires, all of the suppliers nowadays will be able to demonstrate, their solder wires, and you can look at the performance, and you can do simple tests yourself where you add solder to a soldering iron tip through a hole in a piece of white paper. Very simple, but it works. And you can see the effect of spitting. So you can see where the flux actually disappears to, and also where the solder balls appear on the white sheet. So that's a very simple, very crude way. This video clip, which was made by Japan Unix, using high-speed. I love high-speed video cameras. They're just such a beautiful tool to use. And the guys have used high-speed here. So if you watch on the right-hand side, you can see there's a fair bit of solder balling, which is not obvious at all on the left-hand side. And this is all about the wire preparation. And this is something that I learned early on with one of my projects. Basically, if you've got a volatile material which is sealed within a lump of solder, as soon as the solder becomes a liquid, there is an expansion, if you like, of gaseous material from the surface, which can lead to solder particles being spat around, which does happen. This example cross-section here is from a small company in Japan who developed a simple method of V-scoring wire. So they did this for hand soldering operations during the introduction of lead-free. And they used this particular technique. You'll find that the majority now of robotic soldering systems, be laser or contact soldering, in their feeder mechanism have a blade which indents the wire. Now, I choose to believe, I may be wrong, but I choose to believe that originally, whoever came up with the methodology for feeding wire sort of stumbled across the potential for eliminating solder balls, and then everybody else followed suit. A personal opinion. That's my take on it all, but it's been developed very well by different suppliers. So these are photographs of mine where I've got some wire, it's been indented, but what I've also done is I've x-rayed it so you can actually see the core. So obviously, as you know, with an X-ray, if you've got a solid material, it's kind of dark in color. If there's a void in it, it's kind of light in color. So you can actually see the void line where the flux is, but you can also see the indents within the wire which are present. And what this does is allow the volatility to escape during the soldering operation without projecting solder balls over your product. So this little video clip just highlights this with Polyseco on their system. But also, if you look carefully with this high-speed video that they produced, you can actually see the liquid or the flux coming out of the holes prior to going onto the soldering iron tip, which minimizes the possibility of this volume of material being spat out on the surface of the board. So it's just a nice example. Now, Bob Willis, I always have to do it a simpler way. This is a little experiment that I did just on a ceramic plate. This is just a normal ceramic plate that you might use for solder paste evaluation. And if you've got no indents at all, so no indents at all, you will get solder balls. And the solder balls you'll be able to see on the surface of the the white ceramic, and that's the reason why I used it. If you look at this example, this video clip, you can see on the right hand side, you can actually see the marks on the surface of the solder. So if I do exactly the same, run the video clip, you'll see the solder liquefying on the surface of the ceramic. You can see the flux coming out, but there's no solder balls. So again, that releasing that energy early reduces significantly the volatility. And again, you can see exactly the same thing happening on this example. Third example is the solder wire again, but I'm not reflowing it. All I'm doing is heating it up. So in this example, what you can see is slowly the liquid coming to the surface on the surface of the wire from those indents. So that indentation is quite a crucial thing. So controlling that, making sure that works successfully. And again, most equipment manufacturers have the capability of modifying the amount of indentation or even changing the wheels which create it in the first place. So that's just something, a little thing that you want to be aware of. Now, if you're looking at temperatures and measurement, I said to you about using nitrogen. Well, controlling the flow rate. Now, some solder iron manufacturers systems who are used on robotic systems have developed their technology to allow nitrogen to be introduced around and across the surface of the soldering iron. And if you can do this and controlling the flow rate of the nitrogen, then you can use that as a preheat. So you can perhaps get an improvement in terms of soldering parts of a second, but over a day, that's minutes. So again, that's something that might be advantageous to you. But that preheating exercise can be beneficial. So introducing nitrogen across the surface of the joint and the soldering area has two benefits, which you can see in these examples. Also, the angle, the way in which you introduce the solder to the soldering iron tip or to the rest of the joint can be analyzed, again, using IR technology to do the measurement. So if you have a system, I think use it because it is beneficial. And I apologize that everybody will be rushing out and buying an IR system. So if you've got a budget to spend, that's something that's a useful tool. And if Fleur want to send me one in the post to use, I'm more than happy to receive it. Anyway, moving on. So if we look at spitting and spattering of solder onto the surface of a printed circuit board, we need to, try and eliminate the problem by using the best wire available, but also by looking at indentation and the effect it has during the soldering operation. But we also may want to look at spread as well. So we can do spitting patterns fairly easy on the surface of a nickel gold plated test substrate. We can design a substrate here with moldable circles. So you're soldering to the small one, and then you can look at the spit out rate, how far the balls actually go and how many balls to do an experiment. And also you could use a sort of another simple technique where you're actually measuring flow rate. So just like my wetting indicators I use in reflow technology, you could use a pattern where you're introducing solder to a test pattern of some description and then looking at the spread out rate for different parameters, different nitrogen levels, different cord wires that you're using. So there's so much more you can do to optimize a process. This is an experiment. It's pretty much the same sort of thing that the guys at Japan Unix did. And you can see here they've got copper tiles or copper circles. So they're introducing nitrogen to the surface, which is preheating as well as introducing a nitrogen environment to OSP. And you can see just a comparison. I don't read Japanese, so I can't give you all the details, but I understand some of it. So again, it's just another technique to optimize the process, to understand what we need to do with our process. Now, in terms of soldering irons and designs and tips, then you've got to look at the temperature response time. And again, there are tips suppliers and suppliers of soldering irons themselves who have better responses than others, and that's something you need to evaluate yourself. But also the important thing is that if you are mechanically scrubbing the board, if you are mechanically making contact with the board and putting any pressure on the tool, potentially you can reduce the working life. So where you're able to minimize that a wear characteristic, then you get a better working life, and you're not going to run out of tips quite so quickly. Also, you need to evaluate the tips. Some tip manufacturers are exclusive to a particular supplier, and for good reason, because of the calibration and traceability. But again, you need to understand that when you're selecting a system, because it can be an expensive commodity when we're talking about tips and tip replacement. Now, in terms of cleaning tools, there are a variety of options, and basically a cleaning tool is similar to what we do with a soldering iron. You either use a sponge, a moist sponge, which is still my preference, I have to say, if used correctly and you train your staff correctly. But there are other techniques, and I just wanted to show the sponges, the brushes, air jet, where you're actually blowing off residue from the surface of the tip. So there's 3 or 4 different technologies that you can consider, but it's certainly something that it is necessary as part of your work cell for your soldering process. So evaluate them to see what works successfully for you. Okay, so just looking now a little bit on the sort of soldering and soldering results side of things. I wanted to show you some information based on the trials we did with the higher temperature materials. But before that, I wanted to go on to our third question. And our third question is, what do you expect? What is your aim? What do you need to do with your current soldering process in terms of inspection? So what class do you expect, do you require of your product? So what is the most common class that you work to on products today, and or you would equally require from a robotic soldering system? So we're up to 50% so far. So just add your results, click on the button, class 3, class 2, class 1, or don't know of IPC. That would be great. We're up to 70%. Okay, we're just over 80%, so we'll stop it there. So reminder, I will be sending these results to you later on today. So in terms of soldering, I produced joints with selective, intrusive, hand soldering, laser and contact soldering. And the laser and contact soldering samples were produced by a number of different companies. So just a little bit of background information. You can read the reports as well if you want to download them from the MPL website. But this is just an example of the joints. The selective is there, but we've actually got laser joints as well. In terms of when we examined the joints after producing them and then thermally aging them, we obviously saw changes in the characteristics of the joints, mechanical strength of the joints, etc. And of course, we saw changes in the intermetallic thickness based on that storage time. And the storage time was just a comparison time and temperature that we were using for some other studies. But you can see the difference in the results that we saw just on the intermetallic level. And I've shown it for the different alloys. Now, this is an average of multiple samples, but you can see the soldering process and the material we were actually using. So it just gives you a feel for what you might expect to see. And some of the samples, as I said earlier, we went through temperature cycling as well as part of a separate part of this project. And then what we did, just to compare, and this is something that some companies still do, which is doing pull strength measurements and assessment of joints if they're changing their process, so if they're going to an automated process as opposed to hand soldering. So you might choose to do this as a method of comparison if you're looking at laser, contact, selective, etc. But the two failure modes that you would normally, well, there's actually three failure modes that you would normally expect to see if you were doing pull testing. One, you pull the whole bulk of the joint up out of the plated through hole. You normally leave the pad behind on one side, as you can see here on the left-hand side of this particular slide. On the right, you can see where we pulled the pin out of the bulk of the solder. And this is normally where there's a high intermetallic formation or some other factor has affected the surface plating on the pin itself. The other third failure mode is the pin breaks. And generally speaking, when I'm doing testing of through-hole terminations like this, it's normally the pin breaks. But after aging, this is the two types of failure modes you might expect to see. So just so you can see, these two images just show testing. First of all, these are both slow motion, so you can actually see the barrel of the joint, the whole joint being pulled out of the board. And in the second example, you can see the pin being pulled out of the joint, as I've already shown you. And I've given you some results before and after, just as a comparison. As I said, not everybody does this sort of stuff anymore, but it's just a useful to understand what is the difference between the two. So the next section I want to go on to is some defects with laser and contact soldering. But before that, what I want to do is do the final survey with you, and this is about the materials. So what solder wire would you like to use if you were going to laser or contact soldering? So is it tin lead? Is it lead free, traditional 220 to 230, low temperature if that was available, or high temperature for some applications? So which solder would you generally be wanting to use with your robotic soldering system? So we're up to 57% of people voted. We're over 70%. And as I can see, the majority of people want to use just a traditional lead-free. We're up to 83, 85%, so we've closed the survey at this moment in time. Thanks for participating in the survey. Just useful. You can use it as a reference when you're discussing with colleagues. So we'll go back and look at that results when you get them from me later on. So we'll just pick up on some common defects and I can discuss those. So first of all, this is whole wall pull away. Now, you tend to find with certain high temperature laminates, if you don't get the preparation of the surface of the base material correct prior to plating, then during a soldering operation or even a solder leveling operation, you might get some evidence of whole wall pull away. Now, when we went to high temperature laminates during the introduction of lead-free materials, I'm just talking about the versions of FR4, if you like, we did see this particular phenomena. But PCB manufacturers understood the problem, improved the problem, so that sort of kind of went away. But on some of the boards that I processed, some of the polyimide base materials, we did have some problems of whole wall pull away. Not complete from all surfaces, but there was some evidence of it. I also saw some whole wall pull away on joints that I had produced using laser soldering. And I believe what was the mechanism by which the failure was occurring is the parameters we were using for the soldering operation. So I felt that the preheat time, the energy being used to preheat was okay, but the issue was the amount of energy for the reflow soldering operation. And remember that some of the materials I was using were high temperature, so high temperature for reflow of these alloys. So I did see that. So whole wall pull away, separation of the copper within the bulk of the material. But again, maybe material related, maybe temperature related. But again, it's something to understand and evaluate Now, these defects and other defects are covered in my video of the month defects, and also they're covered in the NPL report. Now, pad lifting and fillet lifting is something that I have seen on a number of occasions during the introduction of lead-free technology, and also during this particular exercise. And it is not uncommon. And the interesting thing is, when we look at pad lifting, which I show you on the left-hand side, you know, this was happening in sort of the late 60s and 70s on thick multi-layer boards. And there are reports out there, if you go to some of the early work in laboratories, in this is tin lead technology, it's just the board expanding and contracting during the soldering operation, and the solder wets the pad, but as the board contracts back, it separates, so you get this lifting phenomena. In terms of the solder lifting off the pad, which you see on the right-hand side, what we call fillet lifting, again, it's the mechanics of the solder. As it solidifies at different rates and different positions within the barrel of the plated through hole and on the surface of the pin. And you do see this. This is not necessarily a widespread issue. It's just something you will see if you look hard enough. It's just like we never knew we had voids until we bought X-rays systems. The same thing, if you look hard enough, you'll probably find it. Again, there is guidance in the IPC standards, IPC 610, for fillet lifting and pad lifting. So it's something you will still see with robotic soldering. A robotic soldering supplier blamed me, said, "Oh, you shouldn't say this, you know, this doesn't happen." Well, it does. Not all the time, but it does happen in the real world. So again, if people are aware of it, they can make their own call. So again, another example of a defect. Onto solder balls, and I've mentioned this a few times, and it's sort of kind of one of the things that you may well see, depending on how you set your process up and materials you use. But 9 times out, it's just spitting from the surface of the soldering operation, which I've shown you with some excellent videos, high-speed videos, and going my simple experiments myself, where you can see the impact of indentation in the solder wire, the release of the energy, minimizing the solder spitting and spattering during the soldering operation. Okay, so robotics. Yeah, robotics and scuba diving. So it's 2 things I love. Well, scuba diving I love, and then the robotics is kind of a sideline at the moment. So what I've tried to do in this webinar is just give you an introduction to the technology, talk about different parts of the process, what I've been doing, where you can get other information, etc. So what I want to do now is take any questions. So hopefully there is lots of questions that I can pick up on, and I'll try to do the best I can in terms of answering. Amber asks, are the square pins for wire wrap? No, not necessarily. You'll find some connectors are still using square pins for wire wrapping. Yes, but you know you find them on connectors. It depends on the generation of the connector, I would suggest to you, but it tends to be oblong pins more. Just to mention on the pins, a friend of mine who has worked with robotic laser soldering over a number of years did share with me sometimes you get issues of reflection. So sometimes you can get a pin surface which are actually, when you're setting up the laser, to impinge on the surface, you can get reflection. And he actually had a problem with a particular board or a component which was adjacent to the pins, and he actually got some damage to adjacent sections. But again, any company that's providing laser technology for you will be able to give you guidance and input on that. Okay, let me just go to next question. Okay, can you Okay, so Tim, a little bit about whole wall pull away again. So basically, if you take a solder joint, if you hand solder a joint and hold the iron on there for, let's say, 30 seconds, there's always the possibility that you're going to damage the plated through hole, the adhesion of the copper to the barrel. But on the examples I showed you, because you've got a differential expansion between the copper barrel and the rest of the plated through hole, or sorry, the laminate material, you can get this separation. And it all comes down to the preparation. So if the copper adhesion to the wall of the plated through hole, or the metallization, or one part of that process is not working correctly, any energy you put in can cause that separation. But in the case of laser, or in fact contact soldering, if you're using too high a temperature or too long a contact time, you can get this separation. So it's not unique to this process. It's just a fact that it does happen. In terms of where do you get the videos, all the videos, if you follow the links on the slides when you receive them, you can get all of the Defects of the Month video clips there. Or if you just do a search online, Bob Willis YouTube channel, miss out the cricketer, because apparently there was a famous cricketer, so my father used to tell me, who played for Essex, where I still live, who's also called Bob Willis. But, you know, if you just go for me and a guy with no hair, then I think you'll pick up who he is. Any idea on tip life, tip time for robotic soldering? I think, good question. You can't generalize. I wasn't doing enough soldering experiments to see any significant difference or wear out of the tips that I was using. But we're talking about hundreds of solder joints that you'd be producing. Some of the software that is incorporated onto some robotic soldering systems can gather an incredible amount of data. And of course, then you can use that in your QC system, quality control system, to analyze the performance of tips. So again, you know, use the technology, but again, ask the suppliers. The suppliers will give you a guideline, but again, it will depend on temperature, pressure, type of solder alloy you use, etc. So it's very difficult to give you a number. Have you seen robotic soldering used on SMT? Yes, I've done some experiments with surface mount terminations, but only really on simple parts. I haven't really done it on ultra fine pitch. I've only done it on 50 thou pitch parts and resistors, capacitors, but mainly it's been on through hole. So yes, suppliers can do it. So again, speak to them. Can you use indented wire, also useful for manual soldering? This is Arnold. Good question. Yes. Originally, if you go back to what I said about the V-scored wire, originally from the Japanese supply, that's what he was making it for. So those systems indented the wire, and he was using it for the soldering process. There are two soldering iron manufacturers who offer wire feed systems for their hand soldering and hand soldering tools. So if you do a search for the popular hand soldering equipment suppliers, they'll be able to point you in the right direction. But I'm sure a robotic guy will sell you one as well, if you want to ask them. But yes, it can be used. So again, it's something to think about. But in hand soldering, I think, in all honesty, look at the alternative wire suppliers out there. You should be able to get a wire which has a better performance in terms of spitting for hand soldering. Yes, you can use a tool to overcome the problem, but don't use it as the complete answer. Look at two things, because, changing your solder wire may be a cheaper option. So look at both. What is the relationship between sensor placement within the tip? Well, in terms of performance of different soldering iron tips, that's something you have to do as a comparison yourself. You'll find that some of the developments which have been put into the newer tips from different suppliers is quite incredible. If you think about the step change in soldering irons, if we go back, let's say 15, maybe 20 years ago, we had 2 or 3 suppliers of equipment. And then there was a new supplier came onto the block, and that was a real jump in soldering iron tip control, temperature, etc. And since that time, we've had other developments. So there's a lot of different developments out there. So I would just evaluate the different suppliers to get the best performance, or see what you can get from the best performance. Right. Right. Alexander is asking about what major characteristics would you monitor in the process? Well, I mean, fundamentally, the first thing is obviously the solder joint. And if you know the parameters you've used, then you'll do the experiments and you're going to see what fluctuation may occur. You want to look at variations in temperature. So some of the machines will give you that data back from the soldering iron tip, the rise time, etc. It's best to do it independently. Back in the day, I used to do thermocouples using, data loggers, just like you would do with reflow technology, and there's things you can learn from that. But in all honesty, using IR, it's just much easier to check. So there are a variety of different things, but I've indicated a couple of things when we're talking about spitting, wetting characteristics on sample boards that work quite nicely as well. Right, that's really Grant. That's really a commercial question, and it's sort of kind of unfair for me to give a comment. I would say if you're looking at sort of like a basic machine, you might be looking at somewhere between 25 to 30,000 pounds UK price. That's or dollars. And we won't worry about the little differences, but approximately. But please just have a word with the suppliers, just so you've got a feel for it. I don't want to go out to turn and quote prices, but that's an approximation. Would be mainly SAC 305 wires? We decided same. So yep. Personally, I like to use the same solders wherever I can in the process. However, today with a mixture of low temperature materials that we can use, you can optimize your process with SAC alloys and low temperature. And get benefits on reduction on cost, materials, etc., and improve reliability. But yes, it's simpler if everybody uses the same materials, but it does narrow your choice, perhaps. You will find a lot of guys on hand soldering will use tin copper wires, and tin copper wires work very, very well. I mean, there are a number of different suppliers out there for tin copper wires. Yes, you've got a slightly higher temperature, but it's not significantly different when we're talking about hand soldering. Okay, Walter's asking how much tip loading do you recommend? The problem is that if you put a number into some of the machines, it's difficult to say what that number actually is. So yes, you can put a certain loading, a certain number in, but what is actually happening? Wherever possible, what you want to do is reduce completely the loading onto the pad. If you put pressure onto the pad and then leave it in contact for a long period of time, or you lose a higher temperature, you can damage that pad, you can lift that pad. So what you're trying to do is minimize and make sure it's the solder on the soldering iron which is transferring the energy. It's exactly the same as hand soldering. A lot of people scrub the soldering iron tip on the surface of a pad or a lead and think that heats things up quicker. It doesn't. It's the transfer of heat from the soldering iron tip through the solder in liquid form on the surface. If you try and experiment with a soldering iron tip with no solder on, and then a soldering iron with solder on, and measure the temperature rise, you'll see the performance change quite significantly. So again, it's looking at what and how you're doing it. Gerald's asking proportion of cell setup to inline setups. How do you say? I've only seen 1 or 2 inline systems. And I've worked on 2 within automotive manufacturers to improve, results or improve speed and all those sort of good things. So I've seen inline and benchtop systems, but there's opportunity for both out there. I've seen solder balls around SMD pads. My guess was the footprint was too small. Well, this is really a reflow. This Jesus, this is really a reflow question. I would have thought from your description. When you're looking at solder ball problems on PCBs, if you send me a photograph, I probably would be able to suggest where it's come from. Again, that's not because I'm knowledgeable, it's just I've got a lot of experience. So I'm an old guy. So I think it's a solder paste issue, not a sort of a contact soldering issue. Okay, it's a good question from Michael about bringing robotic soldering in-house. I think that sometimes when you look at processes, people step back and say, do I need it? And in the case of robotic soldering, just to go back on the question that was asked before, the investment on a small system to learn the technology, learn the programming, learn the potential performance, I think it is very worthwhile. And sometimes you can't justify it on a return on investment on a particular product. But learning a technology early, it's just like surface mount, learning a technology early, and then you iron out the bugs before you actually invest in it and need to rely on it to produce in volume. So I think that it is worth the investment. And there are lots of good robotic systems out there now that you could take advantage of. Is there a possibility of using this technology for touching up PCBs after wave and selective soldering? No, I would suggest not. The reason being, it's more complex than that, because you've got to tell the machine what's a good joint, what's a bad joint. You've also got to tell the machine how much solder to add, how much solder not to add. So I can't envisage that in the short term there's a benefit, because the programming time, the setup time, the changes would be just too much. There used to be, back in the day, and we're talking about 25 years ago, a system which would inspect joints with X-ray, and based on the volume of solder, the void that was there, it would actually rework joints. But that's sort of another technology which unfortunately didn't pan out very well within the industry. But no, I can't really envisage it really working. Do you need a dedicated? Do you have a dedicated profile per combination of PCB and component? Yes, I mean, if every one of those joints, is the same, I would probably say no. You would use a temperature and time which might be slightly higher to allow for the variation. If you take a connector like the one I'm showing you, it is inevitable that the contacts nearer to the connector body, so the row near to the body, will take slightly longer or slightly higher temperature to make a joint. The row of joints away from the connector body, so right on the outside of the one I showed you, they'll be easier to solder. But that's sort of, fractions of a second and a couple of degrees difference. Where you've got to accommodate different thermal demands of joints, then again, you've got that variation. So I think that you will tend to find a combination of temperature, time, that suits that whole connector. That's my gut feel for you. But if you've got one particular contact that you can't get whatever standard you're trying to meet, then again, you will adapt it. Okay, in PB3 world, got an info saying a small content of FE has a direct impact. Right, it's Christian. This is talking about additives to cord wires to improve soldering iron and soldering iron tip life because of the erosion of tips. There are materials out there, as you have obviously indicated. I have no specific experience of doing a comparison of the materials. Sorry if that's sort of not what you wanted to hear, but you really need to do a comparison yourself. And I would talk to the supplier. I would get some samples. I would work with 2 production team members on the shop floor and do some form of long-term comparison yourself. But yes, there are additives added to improve tip life. But the first thing is to make sure the tips are good to start off with. Now, most tips from suppliers are consistent, good quality. Today, if you step back a few years, particularly during the introduction of lead-free technology, there were some awful quality tips out there, awful quality plating out there. And of course, they disappeared with the introduction of tin silver copper onto joints. So again, it's all about the quality, but also monitoring the process and comparing the materials if you wish. Okay, this is Javier asking about my experience with laser soldering on through-hole solder joints with preforms. I have not used preforms that I am familiar with, and obviously you are familiar with either of these types of systems so far. No, I haven't. I believe that if they're flux coated, I think that you could use them effectively, and as long as the volatility issue is not an issue with the coating on the preforms, which if you've got the powder coatings on the surface, they're not preforms that have been created with flux inside the preform, like press preforms, I think that should work perfectly well. Okay, I just got time to take 2 more questions. There's probably another 6 or 7 which I will answer afterwards, but I just got time for a couple more. Have you noticed any difference between soldering from above or below the board? Components are upside down or not? It's interesting. One of the systems I used was the Firefly. It's a system came out of Italy, I believe, and they can configure their system either way, top or bottom, obviously depending on the product. And the answer is no. And some of the boards were processed on the top, and some were processed on the bottom. And this was not because I chose to evaluate that question or that issue, just purely that's how they were set up when I did the trials. But no, I can't envisage necessarily any issue with top or bottom. I'd love to hear if you find that you had a problem. What is the shelf life of pre-indented wire, indented now, used later? That's a very good question. I've got wire here that was indented in 2014 that I've still got and used today for tests and evaluations and things like that. I'm not saying you should do that, but remember that the wire is indented on the machine. So you're indenting the wire as part of the feeding process. And I'm sorry if perhaps I wasn't as clear as I could have been. So it's not really an aging thing. When we talk about feeding wire with hand soldering, again, those tools indent the wire as part of the feeding operation onto the machine, so there really is no delay. But the wires that I have were indented specifically for me, so I had them for doing the videos that you've already seen and other comparisons. And as I said, I have still used them since 2014, these different wires. And I had tin silver copper, and the higher temperature alloys, the tin antimony, the lead tin, etc. So, I haven't had a problem, so I don't believe that you would either. Okay, so as I said, there's still a few more questions, but unfortunately I'm just really running out of time. But I will follow up those questions and give you answers. So what I wanted to do, just thank you all for participating in this webinar. I hope you've enjoyed it. I haven't actually seen another webinar on robotic soldering, and I'm really looking forward to doing another one after we've done our robotic soldering experience. I will be sending you a copy of all of the slides within sort of an hour, 2 hours of this end of this webinar, and I will be sending you the results of the polls, possibly after that, just depending on timescales here in the UK. And all I can say is please visit the website, find out about the different soldering experiences that we're running and looking after, and hopefully we can work together on robotic soldering in the future. I've still got more to learn. I hope you've still got more to learn, and it's a great technology, and electronic manufacturing is great. I enjoy it, second only to scuba diving and playing football. So once again, thank you very much for joining me this afternoon. Thank you very much, and good afternoon to you all. Good afternoon.